I'm going to do the absorption of this aluminium 2.01 millimeters. So can you record that? Yeah. Let's place it in front. Okay, check. Okay, ready? For 30 seconds. Okay, 3, 2, 1, count. Five, 4, 3, 2, 1, stop. Okay? I'm going to put 4, 0.49, 0.49, 0.49, 0.58. Work out the count rate and then work out the corrected count rate. Okay? And then we'll look at your results and then see if we have some sort of relationship.
Thank you, Mr. Hamid, for doing this experiment on the absorption of beta radiation using aluminium. We're going to analyze the results now, but before we do so, this experiment is governed by this equation. And as you can see that this equation has the function of exponential. So it's an exponential decrease. How do we know it's a decrease? We've got that minus over there. But what do each of these quantities represent? I is the intensity, right? So your Geiger-Müller tube is actually picking up how much beta particles are coming out. So your intensity, in other words, here is also the same as your count rate. So that's the transmitted intensity that's going through the thickness of that aluminum plate. X is that thickness. So we're varying the thickness of the aluminum. I naught is the original intensity, the directly proportional to the original count rate. Oh, on the subject of count rate, this is really very important. Mr. Hamid had done it at the start that whenever you do count rate, there's something else called the corrected count rate. The corrected count rate takes into consideration background radiation, which is an error, and you've got to take that away. Now, there are this quantity. So the aim of this experiment is to work out mu. And what's mu? Mu is called the attenuation coefficient. In other words, and there's another name for it. People can call it as well absorption coefficient, which means how much did it absorb the beta. When x is equal to half, that means the intensity has reduced. So the intensity becomes the original intensity divided by 2. And that the original intensity stays the same, E minus mu, but the x that makes your transmitted intensity half is now given the name of x half thickness, right? You can see the I naught crosses out. I'm going to write half using indices, which is 2 to the power minus 1 is equal to E minus mu x half. Reason why I'm doing that is I'm going to apply log. And when you work with exponential, you need to apply log to the base of E, which is ln. So if I apply ln here, that becomes ln 2 to the power minus 1. And we know powers go at the front. So that becomes minus ln 2 is equal to ln E. And the power comes to the front. Ln E is 1. That comes to the front. I'm just going to do it in one line. It's not a maths lesson, so you should know this. This is minus mu x half. Okay? So the minus crosses out on each side. You'll end up with mu is equal to ln 2 over x half. Guys, the objective of this lesson is to work out mu in 2 ways. It's the same experiment, but you're going to plot 2 graphs. And I'm going to show you that now. So I'm just going to put the results that we got for our class. So this is the results for our class. And if you plot that intensity or that count rate with x, you get this. So this is the first method. How are we then going to work out mu? The first way. So first thing you do your curve of best fit. You'll do your curve of best fits. And notice that this is an exponential decay. An exponential decay hits the y-axis because it starts with I naught, but then it's supposed to be an asymptote there because it never decreases to 0. This is your count rate, and this is your x. So this value here is your x half. Why is this x half? It's because your original intensity was here, and it became half. And the x value that did that is that. So that's one way you could get mu. You would read the value for x half, which I think it is that's 1.5. Let's say it's around 1.6. So x half is 1.6. To work out then coefficient in absorption coefficient, you then do ln 2 over 1.6, which is around 0.693 over 1.6. And I don't know, you'll get a value. All right? So this is our table of result that we've got. What I'm going to do now is I'm going to do a different method. So can you think of a different way to work out the value of mu? Right? I'm going to pause the video if you can and try and work it out. How do you then modify this set of results to satisfy the new graph? And use the box. I'm going to do that. So I'm going to do that now. Okay. So the new method here is using log. So what I'm going to do, again, log to the base of e becomes ln. Ln I is equal to ln I naught. And when we apply logs and they are multiplied, there's a little multiplication here that you can't see. When you change them to logs, it's added. So that becomes ln e minus mu x. We also know when something has got ln e, that's 1, and you bring the power to the front. So that becomes ln I is equal to ln I naught. The power comes to the front, so that becomes minus mu x multiplied by ln e, which is just 1. Okay, what's what I'm going to do now? I'm just going to rewrite this in this format. I haven't done anything. I've just moved this term onto this side. But this is key. This is very, very important. What we've just done here, we've linearized this exponential. So really, the graph looks like that. If you were to plot intensity against x, but we're not plotting that. If we plot ln I on the y-axis, and I plot x on the x-axis, guess what I have? This would then be my gradient, and this would be my y-intercept. So you do expect a graph to go like this. Why? Gradient is negative. The gradient will then be mu or minus mu, and the where it intercepts, that's ln I naught. So how do we modify the graph? You'll need ln I, and all you've got to do in this graph is change it, this table of result, change it so that you now have ln C. And I did that already for you. So if you plot ln C against x, and I've used Excel to do that for me, you get a value of that, 0.4, because the value is directly minus mu. Minus mu, minus 4.2, so my mu, in my particular case, it will be that. And this is very, very important for your paper 3. Thank you.